This is a small, it looks small, but it does a lot of things inside your PC. I mean, actually, you might say this is a PN junction, and this PN junction exactly every activities that is being done. Like you can say, your computer is just made of a PN junction. ICs, even the transistors, and anything that is basically responsible for logic operations. I mean, high, low, high, low. Once it is switched off, it is low. Once it is switched on, it is high. Right? So amplification process that is being there. So your computer is made up basically of these all PN junctions of semiconductor. So today we'll concentrate. This is the core addressing. I mean, this will address the core topic of your department. So I guess we would have started with this first. The course basically should have started with this, but as you are not been introduced to something like potentials or other thing, how to measure that, we have started a bit late, right? So let's see, today's experiment will be diode characteristics experiment. Okay. So let's draw the circuit diagram. We'll have a fixed voltage source. Can you see that? Is that okay? There will be a resistor, and the emitter will be connected in series. Then the diode. Okay, listen. We do know by now what about this three-terminal device, right? You know by now because we have had an experiment on this, right? So that is terminal A, that is B, and that is C, and there will be a fixed voltage source of 12. Now this device, I mean PN, if you look at this closely, I mean I'm giving you, just you may look at this, pass it through. Listen.
PN junction, sir?
Yeah, this one is exactly PN junction. You have learned it in the theory, so you might see this. Okay.
Maybe ash color.
PN junction, can you see there is a black portion?
Yes, sir.
PN junction.
Right? And another gray portion which is smaller. So this black portion is exactly P portion, and the gray portion is N portion, right?
Yes, sir.
So now under normal state, this diode, how it behaves under normal state without having any bias. Right now it is not biased. Bias, that means bias means providing some voltage. Even when you go for transistor, you learn about biasing. So this diode exactly conducts the main activities of, particularly the rectification process. And then for clipping, we need diodes. For switching, we need diode. And almost amplifications, that is also, performed by this. So this has had really, a particular importance that you have to, pay for. So I guess you have to study from book as well as information I am delivering here. So you have to listen to this. Listen. So this is basically made of semiconductor. So semiconductor, a material whose resistivity lies between conductor and insulator. conductor is a particle that, I mean, an element that allows the electron to pass through it. That means there is a gap, and electron can easily pass through this gap. If you look closely inside the conductive material, you'd see that there is a huge gap in between the molecules, and so electron can pass through. So that is what we know as conductor. And insulator is something that has got rigid molecule arrangement. That means there is no gap. So that doesn't allow the electricity to pass through. So the resistivity of this material is too high. You might say infinity. And the resistivity of this is too low. But there is another material in between whose resistivity changes. We can change the resistivity. In different situation, it changes its resistivity. So, and that resistivity stays between these two materials. That is why it is called semiconductor. Either it behaves, sometimes it behaves as an insulator, sometimes it behaves as conductor. For now, this PN junction behaves as an insulator. For now. Okay, let's see why. And it will behave, it will also behave as a conductor when it is forward biased. And when it is reverse biased, it uses as an insulator, right? So that is why it is called semiconductor. Okay, how semiconductor are of, there are different semiconductors like silicon, germanium, right? So this one is of silicon, this one. So it has got 4 electrons in its valence band. So 4 electrons means like you can make, okay, this is silicon, for example, silicon. Okay, where can silicon be available? How can you collect silicon?
Sand. Sand.
Yeah, that's I mean, so the earth surface has got huge amount of silicon. So that is why the semiconductor materials are too cheap. I mean, you can easily, I mean, they are not high cost material, right? And another thing is, you may even make the solar panel using this silicon. Exactly, solar panel is made up of silicon. There is some titanium oxide which is available in the paints. There is a paint color, so that color is of titanium oxide. So you can have titanium oxide over glass, and there is a, I mean, have you heard the strawberry or raspberry? So if you, I mean, put some raspberry on water, so this, there will be a color, right? The color will be basic, I mean, deep blue, right? So that color, if it is mixed up with the titanium oxide, it becomes the color that the solar panel has. So that is how it becomes a anode. And another part, if you write, I mean, if you have carbons on another piece of glass and put it together, it will become a solar panel. So it's very easy to make up. Anyway, this silicon is neither positive nor negative. So it can be made of either positive type or negative type. Okay, how can we make it? Adding up with impurities. That means maybe this jar has got some silicons. Also this jar has got some silicons. Now I will add impurities to that. I would like to make this silicon as p-type and this silicon as n-type. So this silicon will be p-type if we add some trivalent equivalent, I mean impurities to that. That is called doping, right? And if we add some pentavalent impurities to this, it will be n-type. So we have made it p-type and n-type. So p-type has got lots amount of holes, lots of holes that looks like this. And n-type, which is electrons, which is negatively charged particle. So when we combine these together, right? Okay. Right now, these two materials are of like this: holes combination and electrons combinations. So these are two p and n-type material. When we add this together, it will become like this. Let's see what happened in this. Under normal state, we are not yet provided with the power. We are not providing these things with the power. Before we provide it power, once we make a sandwich, what will happen to that? I mean, once you add these two things up, so there is a junction point, right? Okay, let's see. So there is a holes of positive and electrons of negative. Okay. So under normal state, what happens? Right? This PN junction is right now under normal state because we are not providing this with a power. Okay. For now, this positively charged, we know, I have talked about this in the first class, that the two opposite charged particles attracts each other. So here, these holes are positively charged particle, and these electrons negatively charged particle. So they attracts, right? So somehow they would like to mix up with each other. So and got diffused. So what happened at the very junction terminal? So this is the junction point, right? At this junction point, some of the holes got diffused with some of the electrons, and they make a neutral area, and that area doesn't allow the others. It develops an electric field, and that field opposes the other particle to come. So that makes a barrier, and that field is always I mean, expressed in terms of voltage. So that is why if we would like to, I mean, remove the field totally, we need for silicon it is 0.7 volt. If we apply 0.7 volt, then this field will be removed completely, and then the electrons will move, and there will be flow of electrons in it. So until we provide 0.7 volt, it is under normal state. It is no longer allowing the electricity to pass through that. So this barrier is called potential barrier. Okay, because due to some of the electrons got mixed up with some of the holes, and they become a neutral area with an electric field, and that opposes the others to combine. Got it? So that is what is happening under normal state inside a diode. Okay, right now, if you take this diode and place it to somewhere in an electric field, other electric field, that means a battery. So battery has got positive terminal and negative terminal, right? So positive, that means lots of positively charged particle over here and lots of negatively charged particle there. So if we connect this P type with this and N type with this, what will happen? This positive will repel this positive, right? And it will push them towards this junction, right? And this negative will also repel this negative and push them towards this junction. So somehow this junction, if the force is up to 0.1, it will not it's not gonna break. If it is up to 0.2, no, it's not gonna break. So somehow when it will reach somewhere around 0.7, only then this wall will be broken completely and the electrons will flow. So our job today is just to apply different voltages. We'll start from 0.1. First of all, we will apply 0.1. So let's draw a table. This table we will make today. Okay, listen. So that is forward voltage VF, and that is forward current. Why this one is called forward voltage? Listen. Why this one is called forward voltage? Because while we are connecting, listen, while we are taking the values, the diode is in forward bias state. This is, can you see? The P type of the diode is connected somehow to the positive, right? And N type of the diode is connected to negative. That is why it is in forward bias state. Got it?
Yes, sir.
Okay. So we'll apply some potentials and observe what will happen. Exactly, our job is just to find the characteristics of a diode. So how the characteristic means once we apply some voltages, potentials around it, how it behaves, how it reacts to that, right? So first of all, we apply 0.1 volt over there. At 0.1 volt, what will happen to this? This barrier is too high. This wall is too high, right? too strong, it requires some 7 Newton force, maybe, right? It requires some 1 Newton of force over there. This doesn't make the wall broken, right? So there will be what? There will be barrier still at 0.1 volt applied. Got it? Yes, sir. So that means we will have no flow. That means current will be 0. Got it? Yes, sir. Again, we will increase the force. That means once we increase the force, there will be more positively charged particle pulling to the junction. Again here, the more negatively charged particle pulling to that junction from that end. Hey, announcement is there for you. Next week will be your exam. First term exam that consists of 20% of marks of total 100 marks. So you have submitted the report, right? Yes. So the question of that exam will be based on my lecture. I will ask questions. That will be Viva exam and practical exam. So I will have this module with me. I will ask you to make connections. I will ask you to how to measure that, how to measure this, how have we done this, that, different thing. And the question will be based on what I am delivering here. So if you gossip backside somehow, that will, I don't know how smart do you think yourself talking backside when I'm delivering here. So that is not something you are supposed to do. Because based on this, we'll work here. If you do not understand this, you will not be able to perform here. So be careful about this. Okay, listen. An exam is not the matter of fact. The fact is you need to learn this. Yes. Right? Okay, then once we increase the force, that means the amount of positive and negatively charged particle, still it is not enough. So at 0.2 volt, there will be zero current. Current is not, I mean, the wall is not still broken. So it doesn't allow the current to flow. Okay, at 0.3, if we have increased, at 0.3 volt, still there is not enough. Okay, so it will be 0 again. At 0.4, listen, the 0.4 is like, it is getting closer to 0.7, right? So some portions will be broken. Maybe few bricks will get down. There might be a hole like this, right? So through this hole, 1 or 2% can pass. So which means some few electrons can pass still at 0.4 volts. So we'll have very negligible current, maybe 0.05, something like milliampere, which is very small amount. Okay, then we'll increase it up to 0.5. So at 0.5 we'll have some more bricks to collapse. The wall will be collapsing. Wall is right now in the process of collapsing, right? And it is adding up. As we increase the force, the bricks are getting down. I mean, it is collapsing. So that means there will be somewhere around 0.15 or so milliampere. So it increases, right? The amount of electron flow is increasing somehow. Okay, at 0.6, if you increase 0.6, what will happen? This wall will be broken, but not all. Maybe half or 1/3 will be broken. So that means we'll have more than some 2 milliampere current, 2 point something, or even it might be 3 milliampere of current. And from 0.6 to 7, within this range, when it is 0.7, the current will there will be no wall by now, right? The wall is broken completely. That means there is no resistance for now. So electrons will keep moving very fastly. That means once electron is moving very fast, what will happen? The current, that will make the current to increase with a high values, right? Because current is what? The flow of electrons. So once the electron will flow too much, then what will happen? Current will flow. So the current will be more than maybe 15 milliampere, which is too high, right? Okay, listen. So if these values, you have to plot this graph. And whatever I have talked so far, we would like to see this practically. We will see this practically. Got it? Yes. Whatever we have seen here or talked so far, we'd like to verify it practically. That's what will be our experiment. So then that's how diode behaves. And after 4.4, it will be a dead circuit. Dead circuit means a circuit that doesn't allow the current to flow. And after that, from 0.5 to 0.7, it will dramatically change its character. It was an insulator previously, up to this, and right now it becomes a conductor. Right now it is a full conductor. So that is why it is called a semiconductor. It was an insulator at the very beginning, but right now it is a conductor. Got it?
Yes, sir.
So this was zero state and this was high state, low and high. That makes your digital system possible. If there has been no diode, no PN junction, there has been no computer by now. So it's easy, it's important to learn. Okay, let's see. So if you plot, so that is why this characteristics is important for you. So if you plot, the current in the vertical direction, milliampere, and voltage along the horizontal volt. Listen, we would have started, even last year we started the experiment, the first class with the diode. We didn't go for voltage measurement, current measurement, we didn't go for something like potentiometer. But listen, this experiment has got this device. Student would not have understood this. I would have asked question in exam based on this. And they didn't understand that. They didn't answer that. So that is why this year we have planned that we will start at least 2 basic experiments first, and then we'll move to the core experiment. So this is that core experiment. So be careful about this. Again, what happened on the previous years? Students at the very first class or very beginning, they do not concentrate much on study, right? So as days progress, weeks progress, they pay their full attention to this. So that is why some at the very beginning they would not understand the diode. So if you do not understand this, you will not understand rectifier, you will not understand clipping, you will not understand clamping. So there are many of them. So that's where the problem starts. So that is why we have planned it, and be careful about this. Okay. So if you plot, so that was 0.1 volt, there will be 0.2 volt, 0.3 volt, 0.4 volt, 0.5 volt, 0.6, and 0.7, right? And currents are 1, 2, 3, each carries 1 milliampere, right? Like this. Got it? So if we plot, let's see. At 0.1 volt, the current was 0, right?
Yeah.
So there has been no value of current. At 0.2,
Also 0.
also 0. At 0.3,
Again
0. At 0.4, there is some, but there is less than 0. Less than 1. Okay? At 0.5, still it is less than 1, right? And at 0.6, it is more than 2. So that is the 2. It is more than 2, which is here, right? And at 0.7, which is more than 15. So 15 will be even higher, right? So maybe here. Or where is the 7? Yeah. So here, right? So if you add this, make a scatter diagram, what will happen? Is that?
Yes, sir.
So that's how diode behaves. It's an insulator for now, and it's a full conductor. And the stage, the voltage where the diode the current across the diode starts rising sharply is called knee voltage. And there will be a question: what is knee voltage? Okay. And again, what is peak inverse voltage? You will have to learn it. I do not say the answer to that. But what is peak inverse voltage? Right? I'm giving you an idea. Peak inverse voltage is used for safety and security of a diode. So actually, at the reverse region, if we increase the voltage, this is the forward region. At the forward region, if we increase the voltage, what happens? We have seen, right? But at the reverse region, that means if we would have the diode connected this way, that was the reverse region, right?
Yeah.
So at this region, if we increase the voltage here, right, up to certain value the diode will sustain. After that, it will burn. And the maximum value, maximum voltage up to which the diode can sustain itself is called what? Peak inverse voltage. And after peak inverse voltage, the diode will burn. So that is why peak inverse voltage, I mean, the computer, if you connect it with the opposite polarity somehow, against an IC, right, what will happen? Maybe in an IC, the connection is like this, listen. Across an IC and the connection is like this. This is the positive, this is the negative, right? So, but you connected, this one is positive and this one is negative, better negative. So now, right now it is an reverse bias state. So if we apply voltages right now, what will happen? It will reach to its peak inverse voltage. So every IC has got a peak inverse voltage. It will reach to that, and eventually if we increase more the voltages, it will burn. Got it? So that is why peak inverse voltage is important. Okay. Any question regarding this?
No, sir.
Huh? Do you understand this? Okay. What are the components we need to build this circuit? A battery, potentiometer, a resistor, ammeter, voltmeter. So we have learned how voltmeter is connected. We learned how ammeter is connecting, right? We learned how potentiometer works. Up to this question we learned in the last experiment. Then measuring voltage and current we learned. And today we have learned about this. So every component we are familiar with for now, right?
Yes, sir.
And what is I have to talk? Oh, why this resistor is connected? Why? This is diode characteristics experiment, right? Why do we need to learn connect the resistor? Tell me, what would happen if there has been no resistor? The resistor is connected to what?
To
Reduce the flow of electrons. I mean to slower the speed of electrons, so that the current gets slower, and that to control the current and to protect this diode from burning out. Because when there is over current, the diode will burn out. Okay, so exact circuit is like this. Okay,
Sir,
that's it.
We're controlling this.
That's what is voltage is being controlled from here. But this one will control the current, flow of current. Do you understand? I would ask why potentiometer is used. You have to answer because there has been an experiment on potentiometer, right? So anyway, that's it. So for now we will start working with the practical. আপনারা